let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Today, we're going to be working through the quiz that you just did. Hopefully it went okay, but we'll see. So as always, this one is going to probably take a while, so I'll just work through it. And if you have any questions, you can stop me, any comments or anything like that. Let me share my screen here. Someone else is coming in. Okay, there we go. Everyone should be able to see that. Okay, so this is quiz 4. So as I said, I'm going to just go through it. Stop me if you have any questions, and I can also take questions after we get through this. All right, let's do it. So the first couple questions were just checking if you knew some definitions, so we don't really need to actually calculate anything for those. All right. F is a differentiable function. Which of the following is its marginal function? Maybe you guys can tell me that. Which is the marginal function? Right, f prime, right? So marginal function is yet another name for the derivative, right? So in a specific context, we call the derivative a marginal function because it can tell us what's going on at the margins, right? At the edge of production, if you want to push it to one more unit, the derivative is actually a good predictor in some situations. So yeah, the derivative is just another name for the derivative. Which of the following gives us how to approximate f of x at a point x using a linear approximation formula? So the linear approximation formula, this is a whole theorem that tells you when it would work and when it would be a good approximation, etc. However, the formula that appears in that is the second one. Right, so it's the one that looks sort of like the equation of a line, y minus y1 equals mx minus x1. Here your x1 is a, your y1 is f of a, and your m is f prime of a. So it's like you're using the equation of a line, but you're using the equation of specifically the tangent line because your m is the derivative. Okay, so we've seen that. Okay, so here are some indeterminate forms. These are limit forms. Well, actually, one of these is a trick question. So this is actually not an indeterminate form. So if you pick that one, it's really bad. Okay, so infinity times infinity is infinity, right? Take a big number times a big number, we get a big number back. The others, though, aren't clear. Like when you take infinity minus infinity, it could be almost anything. We even did an example in class where I believe the answer to this was a half or something like that. It could be 0, could be infinity, could be minus infinity, could be a half, could be any number in between. Yeah. Which ones does Lotels Rule deal with?
Is it plus or minus infinity over infinity and 0 over 0?
So that's a question I'm throwing out to you guys.
Oh, did you get my answer?
I did not.
Oh,
I didn't hear it.
Sorry, I think it cut out. Okay, so the two choices I chose were plus or minus infinity over infinity and 0 over 0.
Right. So those are the two scenarios that Lotels Rule helps us with. There are ways to deal with the other scenarios, but if you plan on using Lotels Rule, you'd have to convert all the other scenarios into one of these two. So Lotels Rule only works with these two specific scenarios. And if I'm talking and I cut out, you guys should just let me know. because apparently there are some issues here. All right, so now we're at the first problem, question 4, where we do need some calculations. This is using the linear approximation formula, which we already know. So the linear approximation formula looks like that. Right, so this is the one that says f of x is approximately equal to f of a plus f prime of a times x minus a. And x is the value we want to approximate f of x for. A is a nice value. It's nice in the sense that we know it already. We know f of a and f prime of a for. Okay, so x is the value that you're not sure what's going on. You want to approximate it. However, a is a value. It should be close to x. A is a value that's close to x, that is nice in the sense that we actually know what the values it will produce in the derivative and in the function. Okay, so we already know what's going on at a, and we want to use that knowledge to show what's going on at x. And x is something that we don't have any a priori knowledge about. However, we can use this to approximate things that you could plug into your calculator. And so this kind of demonstrates how we would use the linear approximation. So that's what we're going to do. So we want to approximate the cube root of 7.9. Right. So the first thing is we define our function. Cube root of x. And here I would just want my x to be 7.9. That's the guy that I don't know what's going on. So there's going to come a point, not right away, but there will come a point where I'm going to plug in 7.9 for x. Of course, this means if I can find f prime of x right away. Right, so how would I do that? I would rewrite this as x to the 1/3, and I would use the power rule. So the power rule would tell me this is 1/3 x to the minus 2/3, which I could rewrite if I wanted to, optional, as 1/3 cube root of x squared. Okay, so now the second one is I'm going to find my f of a and my f prime of a. So here we're going to use x equals 7.9 and a equals 8. It's a number very close to 7.9 for which I can compute the cube root very easily. I know the cube root of 8 is 2. So that's going to be nice. And so I'm going to find f of a and f prime of a. So f of a is just f of 8. So this is the cube root of 8, which is 2. F prime of a is f prime of 8. That's just 1/3 times the cube root of 8 squared. Cube root of 8 is 2. Oh, I'm getting that message again about my internet being unstable. Let me check something. Yeah, I don't know what's causing that. My internet is, thanks for confirming that it sounds fine, but I got the message on Zoom. So I just wanted to double check. But yeah, my internet's pretty strong. The speed is high. I don't know. I think it's just actually the Zoom app having a connection problem. So yeah, internet is fine on my end, but every now and then I get a message popping up that says, "Oh, your internet is unstable." I don't know. Okay, let's continue. Just let me know if you guys lose me. Okay, so cube root of 8 is 2. I square the 2, I get 4. 3 times the 4 would give me 12. So this is just 1 over 12, right? So those are values that I could see, like off the top of my head, I could tell you what these values are, right? Now 3, we're going to plug into the formula. So we want to use f of x, and again, keep writing down the formula so you don't forget it. If you write down the formula at every opportunity, when you need it, you're going to remember it. So essentially, what we're going to be doing here is we're going to plug this in. So the cube root of 7.9, well, that's just f of 7.9, right? So that's like me plugging in my x. Okay. Now, according to this formula, that is approximately the same as f of 8 plus f prime of 8 times 7.9 minus 8. And again, I'm just plugging in these numbers. My a is 8. Everywhere I see a, I'm going to put in 8. Everywhere I see x, I put in 7.9. Everywhere I see a, I put in 8. And so now I'm going to continue. So f of 8 we computed, that was 2. F prime of 8 we computed, that was 1 over 12. 7.9 minus 8, that's minus 0.1. We were required to write things as fractions though, so this would become minus 0.1 is 1 over 10. So this is 1 over 120. I can create a common denominator by multiplying this by 120 over 120. So this would be 240 over 120 minus 1 over 120. So I get 239 over 120. And that's the guy. That's our approximation. It's the third choice. Five 5.1. I think 5 had several parts. Yes. I don't think they'll take a lot of space to get through, actually. All right. So question 5. PFT is the amount remaining of a radioactive substance after T years. Assuming the half-life of the substance is 230 years, this means the half of the substance decays radioactively, and you only have half of the original type of substance remaining every 230 years. Suppose that's the half-life, and we start with 55 grams of the substance. Answer the following. What equation can be used to find the decay constant? So the decay constant, you just have to remember what these phrases mean. So the decay constant, that means I'm looking for something that's called the R value. Okay, and got that message again, but let's continue. And we actually know from a list of formulas that I gave you that we know how to relate information that we have here to the R value. We know that half-life is equal to ln2 over R, which means that 230 is equal to ln2 over R. So this is an equation where I can find R right away. So that's this one. Moving down, what equation describes the decay rate? So we know what the rate they're talking about is P prime. And we know, or we should know based on the formulas that I gave you, P prime is equal to minus R times P. So from before, we know that this is minus ln2 over 230 times P. And you'll notice that that's none of the above. So option A looks very close, but it's missing the negative sign. Without the negative sign, that models something that's growing, right? We want the thing to actually be decreasing. So the derivative has to be negative. The slope of the curve has to be going down. So the negative sign is actually important here. If you don't put the negative sign, it means you're actually growing and you're thinking of the thing as doubling instead of halving. So that's actually none of the above. So now we know the PERT formula. P is equal to P naught e to the minus RT. And so when we start to plug these in, P naught is the initial amount. This is 55. R we know is ln2 over 230. And there's a T. And that is equal to this one. Right, so these you didn't have to do many calculations for. Like if you knew the equations that I gave you in that handout, you would know how to deal with these without too much trouble. All right, moving on to problem 6. Let me take a here. So remember we learned from our strategies of limits, strategies. It's been a long night. Strategies of limits, that one of the first things you want to do with limits is kind of plug in. And so you kind of want to see how what you're looking at is behaving right off the bat. Here, if I let x approach negative infinity, this will actually approach negative infinity plus infinity, which we know is indeterminate. So we have to rewrite it somehow. And the way you would go about doing that is, I believe I did a very similar example in class, if not the same example, but whenever you want to rewrite these things, you're pretty much just using laws of algebra. So here, a common term is x. So I can actually factor that out. Now you'll notice that this is going to approach, well, negative infinity times infinity squared is going to be infinity minus 1, makes no difference, that's just infinity. So now I rewrote this infinity minus infinity as an infinity times infinity, and that's not indeterminate anymore. We know what that is. A big number times a big number is a big number. So here it's now clear. It's negative infinity. So this here is not indeterminate. And doesn't seem like anyone's asking any questions. At least I haven't heard anything, and nothing seems to be in the chat. So I will keep going. Okay, so 6.2. So consider this limit. Notice that if you were to plug in x equals 0, this would actually approach e to the 0 minus 1 minus 0 over 0 squared. This is approaching It's not equal to, but it's approaching. Well, e to the 0 is 1, so this is approaching 0 over 0. And so Lotels rule does apply. So Lotels rule applies. Okay, so given that Lotels rule apply, how do we actually apply it? Basically, the idea is if I have the limit as x approaches 0 of e to the x minus 1 minus x over x squared, and I know that it goes to 0 over 0 or infinity over infinity, plus or minus, I can apply L'Hopital's rule, and L'Hopital's rule tells me, right, and there are some requirements here, it has to be continuous, right, but you guys don't need to know that because I always make sure that those conditions are fulfilled for the problems that we're looking at. So L'Hopital's rule says if your limit approaches one of these two values, then provided the limit exists, it will give you the same value as if you take the derivative of the numerator and the derivative of the denominator separately. It's a confusion that happens. I wouldn't say it's overly common, but common enough for students to think that they should just literally take the derivative and do the quotient rule. And so that's what the first option here is doing. It just took literally the derivative of what you're looking at by the quotient rule, but that's not what L'Hopital's rule says. You take the derivative of the top and the derivative of the bottom separately. And with the limits, this will actually work out to be the same. So I take the derivative of e to the x, that's e to the x. Derivative of 1 is 0, derivative of x is 1. Derivative of the bottom is 2x. I look for that and I don't see that. So now let me check though. This also approaches 0 over 0, which means L'Hopital's rule can apply again. Differentiate the top and differentiate the bottom. And there's that option. So that was also something we covered in class. L'Hopital's rule, you can apply it over and over. So if you don't get the result you want, you can check if L'Hopital's rule applies again after simplifying and apply it again if you can. You can apply it as many times as you have to. There are certain functions where you have to apply it a lot of times. Consider this limit. L'Hopital's rule applies and the answer is infinity, or L'Hopital's rule applies and the answer is negative infinity. L'Hopital rule applies and the answer is 0. L'Hopital's rule does not apply and the answer is 0, or none of the above. Maybe someone can tell me what's going on with this one here. So this is a conceptual question. Okay, well, you think you got it wrong. Tell me what you thought anyway, and we'll see.
All right. So what I thought was like first, like in order for L'Hopital's rule to apply, it either has to be, plus or minus infinity over infinity or 0 over 0.
Right.
So I tried plugging in 0.
Right. And what happens to ln as you're approaching 0 from the right?
I believe that goes to negative infinity. Like it's not
does.
an actual value.
Right. It keeps going down, right? So you know that
Yeah.
from the graph. And the x?
That's 0.
That's 0.
Yeah,
Which means L'Hopital rule does not apply.
Okay. Yeah, that's what I thought, but I wasn't sure if there's some like trick to it or something.
Right. The trick would be, could I rewrite it so that it applies? Might be
Yeah.
a trick that you would think about. But immediately, everything that says L'Hopital's rule applies is now off the table. So it's either going to be none of the above, or L'Hopital's rule does not apply and the answer is actually 0. Now, notice what we have here. Are you guys seeing me?
Yes.
Okay. So let's actually look at this. Limit as x approaches 0 plus of ln x over x. I could rewrite this. Let me start to separate things. And what would these things approach now?
It would approach negative infinity times does not
One over
exist, or
one over
times infinity,
times
right?
infinity, because it's coming from the right, right? So it's 0 from the right. If it was 0, it would be a does not exist.
Yeah.
However, it is coming from the right. So I know 1 over x goes up as you come from the right. So that's not indeterminate. That's actually negative infinity. So this limit is actually equal to negative infinity. And if you rewrote it one of the other ways, like we saw some tricks in class where we can take the reciprocal of one term and move it in the denominator or move it above, and you would actually get the same thing. If I were to instead of having x write 1 over x and move it to the top, I would end up getting negative infinity times infinity in the top. If I took 1 over ln x and moved that to the bottom, I would end up getting 0 times 0 in the bottom, where it's approaching from one side. It's approaching negative 0 from the negative side in the denominator. And so either way, you can get to this answer. But just actually factoring off the x, you could see this pretty easily. So it turns out none of the above. The limit does, we can determine how it behaves. It does go to negative infinity. But it doesn't do this by Lotels rule. It did this by just me rearranging and thinking about it a different way. But knowing that Lotels rule does or does not apply is very important. You don't want to overuse Lotels rule. I have students trying to use Lotels rule all the time, even when it doesn't apply, because it's such an easy rule to apply. They're always very tempted to just apply it right away, because you can get to the answer in a few seconds a lot of the times, but you can't always apply it. Was that what you ended up picking, Daniel?
Yes, it was.
Okay, so yeah, you got it right. So
Yeah.
and you got it right for, I don't know if you got it right for the right reasons, actually, because I was the one who came up with this idea. So I don't know what went through your head why you picked none of the above, but
I'm gonna be honest. I kind of guessed between the two, and I got it right. So
okay. Well, at least I mean, I'll let that slide. I mean, if you had an educated guess and you could literally know that the first three did not apply, then yeah, I'll let that slide. That's the thing about quizzes. You can get away with stuff like that. Can't get away with that on the test. Like if I had actually asked you to show your work, you probably would have lost some points, but you would have gotten maybe half credit. Okay, this is a related rates problem. So there is a standard strategy for these. So I mean, this problem I'm just going to go through and do that strategy. Even though it might seem as overkill, I would just stick to the strategies for the word problem so you don't get lost. So one is to read. And there's a reason that I put that as a step in the strategy, because as we move on, we're going to learn a couple other types of word problems, and I don't want you to mix them up. I don't want you to mix up a related rates problem with an optimization problem, for example. So read, make sure you know what type of problem you're looking at. I gave you hints in the handout, which you can find on the class website, so that how do you know that you're looking at a related rates problems? There are some bullet points that you can look for. How do you know that you're looking at an optimization problem? There are bullet points that you should look for. Okay, so read very carefully, not only to recognize what kind of problem you're doing, but also to pick out the important information. Two, a diagram can be helpful. Here, we know that we hit it with a rock and we had some pebbles coming out, and there are concentric circles. But we only care about the outer one. So we only actually care about the biggest circle. And we also care about the area of the circle, which is what the question asked about. So this is your R, and the area is the green part. Okay, so that's my diagram. So the diagram helps me with the step 4. So 3, what we like to do is write down what we know and what we want. So what do we know? Pella is dropped in a calm pond, causing ripples that form concentric circles. The radius R of the outer ripple is increasing at blah. So I know how fast the radius is increasing. And it's positive because it's increasing. At what rate is the total area changing when R equals 2? So what we want is the rate of change of area when R equals 2. So now from that, I know I want a formula equation. I want an equation that relates all the variables that connect what I know to what I want. So I want an equation that will connect the R to the A. And because of my diagram, I'm thinking circles. So the equation here is pi r squared. The fifth thing we're going to do is we're going to differentiate. You have to remember it's differentiating implicitly with respect to t. So when we're doing related rates, the rate here is meant literally. It's meaning it's change over time. So we differentiate with respect to t. So t is our independent variable, which means a and r, we think of them as functions of t, which means the chain rule applies whenever I'm differentiating a and r. And so what I would get when I differentiate the a, that's just a prime, dA dt. What would I get when I differentiate this? Well, it's 2 pi r, but I have to multiply by dr dt because that is not the independent variable. And now 6, plug in knowns, solve for unknown. So dA dt is actually what I want. I don't know that, but I do know that my r is 2 and my dr dt is pi. So this means my dA dt is equal to 2 pi times 2 times pi. And so that gives me 4 pi squared. Now I put the units here just to be complete, but I told you guys you don't have to worry about the units. So whatever answer you get here, you should assume that's the answer. So it's 4 pi squared. Don't worry. In physics class, they're going to bother you guys about units, and even in chemistry class as well, because it's super important in those courses. And sometimes the units can even like tell you what you need to do, and so they really emphasize it in those courses. In this course, I don't particularly care about you emphasizing units. Once you understand the strategy, I'm fine with that. Some of your other science professors will bother you about units. I won't do it. Okay, moving on to question 8. The weekly profit from selling X units of a product is given by blah. What is the marginal weekly profit? So remember, marginal is just another name for derivative. So we just want the derivative, and evaluate it at 100. So basically, you reading this word problem, you should realize that that's what you want. We want P prime evaluated at 100. Just another way to write it. So now P prime is equal to differentiate that. That's 50. Differentiate this 0, 0, 6 x, and that's it. So P prime at 100 is 50 minus 0.006 times 100. Multiplying by 100 just means you're moving the decimal place 2 places to the right. So this is just 50 minus 0.6. And so that's 49.4. That's option A. So again, not too bad if you know what the definitions are. What does it mean to take the marginal function? Okay, so there are two parts to this. I believe only two parts. Yeah, so I lost you guys there for a second. I don't think my computer was bluffing. So it's like, yeah, there's something not stable, man. So hopefully you're all back and you can hear me. Well, I think we lost like 2 people. Hopefully they'll join soon. But you guys can hear me?
Yes.
Okay. Yeah, sorry about that. Like it just kicked me off like out of nowhere. Let's actually continue. Let's get through this. Let's try to get through this quickly. All right, so let's stop the dilly-dallying. Okay, you own a computer store. Every time you sell a computer, you make $1,012. Your costs are given by this equation. X is the number of computers sold. How many computers should you sell to maximize profit? So for one, we know that profit equals revenue minus cost. So this means my profit function is the revenue. I make 10, 12 for every computer sold minus now my cost. Someone else is coming in. Okay. So my profit function is going to be minus 4x squared minus, well, actually, now it's going to be 1012x minus 4x. So it's actually going to be plus 1008x plus 80. And that's my profit function. One thing you can know is that this guy here, this is just an upside down parabola. So this is a parabola. This means max is at vertex. So I know for max, x equals minus b over 2a. So that's going to be this over 2 times that. So that's going to be 1008 over 8. 8 goes into 10, 1 time, remainder 2. 8 goes into 20, 2 times, remainder 4. 8 goes into 48, 6 times. 126. Okay, so we have that. Continuation of the same problem. Suppose you've sold 100 computers. Use the marginal cost to approximate the additional cost you'll have if you sell one more computer. This just means that you want the marginal cost evaluated at 100. So again, if you understand the concept of a marginal, you'd understand that this word problem is actually asking you, just find the marginal cost and plug in 100. So our cost was 4x squared plus 4x minus 80. So this means marginal cost is the derivative of this, which is 8x plus 4. And so this means if I plug in 100, I would get 804, which is option B. And that was the quiz. I mean, we have time. Let's just go with the bonus. So these are bonus problems, so I don't expect you guys to have to know this, but you would sort of know this if you started watching ahead. So we talked about critical points at some point after where you were supposed to watch up to. And so what you should remember is that critical points of a function, this means points no. So I had a question about 808. No. So when you evaluate it at the current level of production, the marginal function, it tells you about what would happen if you did one more. So just the marginal function at that point is already evaluating what would happen if you do one more. So you don't have to worry about increasing it one more or something like that. You don't have to worry about manually increasing anything. Okay. So critical points, you'll see this eventually if you haven't seen it already, but these are points where f prime of x is 0 or f prime of x is undefined. Right? And there are reasons why we care about these two kinds of points. I elaborate on this in class, why we care about these particular types of points, but that's the point. So notice here, our f of x is x times 2 minus x cubed. And so I care about where's the derivative 0 or undefined. So first thing to do is find the derivative. I would use the product rule. This would end up being a minus 3x times 2 minus x squared. Let's just put the plus 2 times minus 1. So here, use product rule. Now, of course, this is a polynomial. Note f prime is a polynomial. So it's never undefined. So critical points, if any, occur when f prime equals 0. So now I just go and I want to set that guy equal to 0. This is a minus. Now, in the past, I've had students who try to multiply this out, multiply out the cube. They get this huge thing and they try to refactor, which is not something that you should do. Remember, when you want to, this is something you should learn in pre-calc, when you want to set something equals 0, your main goal should be to factor and use a 0 factor power. You set each factor equal to 0. Here you have 2 minus x as a common term. You pull out the lowest power. I'd be left with 2 minus x minus 3x. So this is 2 minus x squared times 2 minus 4x. And you set each part equal to 0. So here you would get x equals 2, or here you would get x equals a half. So that's that option here. Watching a little further, you would actually also learn about absolute maximums and minimums. At least I think I spoke about this before I spoke about critical points. So the idea is you want to find the largest possible value of f of x on this interval. You're guaranteed to do that when the function is continuous. That's called the extreme value theorem. So there's definitely an answer here. I can't promise you that it's one of the answers shown, but there's definitely an answer. So what you want to do is you first find the critical points. We found them last time. So this was x equals a half and x equals 2. And then you evaluate them. So you find f of a half and f of 2. F of 2 is easy. That's 0 because you had that 2 minus x in there. But f of a half, this is going to be a half times 2 minus a half cubed. That's going to be a half times 3 over 2 cubed. It's going to be 27 over 16. 2, you're going to check the endpoints. The endpoints of the interval, meaning, so these guys here, 1 and 3. So this gives endpoints. So f of 1, you're going to plug that in, right? So f of 1, that's just 1 times 2 minus 1 cubed. That's 1. Then you're going to find f of 3. This is going to be 3 times 2 minus 3 cubed. That's going to be minus 3. And the last step here is to actually compare all of these. The biggest guy is your absolute max, and the smallest guy is your absolute min. Actually, a half doesn't count because this is not in the interval. X equals a half, not in interval. So that would be the biggest guy, but he's not in the interval that we care about. So 1, 2, and 3 would be in that interval. And so of that, the biggest ones are 1. So f of 1 equals 1 is the absolute max, largest value in the interval. By the way, BTW, it didn't ask for this, but f of 3 equals minus 3 is the absolute min. Because it's the smallest value in that interval. So in this situation, 1 is the biggest. Last bonus question. Yeah, we did everything on the bonus comfortably within an hour, so I think it was pretty fair. So let's keep going. What define vertical asymptotes? So this is something that you'll see in class as well. This is a little bit further of a lecture. Vertical asymptotes, here we're going to check where denominator is 0. That's not the main definition, but I mentioned for rational functions, that's equivalently what you end up doing. right? So if you have a ratio of polynomials, that's what you want to do. So you want denominator equals 0 for x equals plus or minus 2. So you look at which one of these denominators would be 0 for x equals plus or minus 2, and it seems like this is literally the only one that even has anything close to that happening. The first one, the denominator is 0 at minus 2. The second one, the denominator is 0 at minus 2. The fourth one, the denominator is 0 at whatever when 3x squared plus 8x plus 8 is 0, which that isn't plus or minus 2. And the last one, the denominator is 0 at 2. So potentially, we know that it's definitely not any of these right away. So at this point, we think it's either going to be that one or none of the above. But that means we have to check for the horizontal asymptote. And we know that the horizontal asymptote, and this you can think of more of a general definition. This is the limit as x approaches infinity of f of x. And you check the limit as x approaches negative infinity of f of x. And we also know that for rational functions, these guys will always agree. They won't agree with every function, but for rational functions, these guys always agree. So you can actually do just one of them. So this is just the limit as x approaches infinity of 3x squared plus 8x plus 8 over x squared minus 4. We know a ratio of leading coefficients, so that's 3. So y equals 3 is an HA. This gives same answer. And just by the limit rules that we've had before. So it turns out that, yeah, this actually does work. Now, of course, everything that I wrote down, you could actually just look at, hopefully you can look at this and tell. Looking at this function, I can see that the denominator would be 0 at x equals plus or minus 2. And I can just eyeball and look at the limits for all of them. So the limit of the first one is 3, but the denominator doesn't work out. The limit of the second one is a third. The limit of the third one is 3. Limit of the fourth one is a third. The limit of the fifth one is 3. Right? So just by looking at our limit rules, we can actually know this off the top of our head. But I just wrote it down so you can know what I'm thinking. So that is it. That was the quiz. Hopefully that wasn't too bad. But we will wrap up there. Unless there are any questions before we go.
Professor, could you go back to question 5.2? I think I must have missed that when I was reviewing my answers.
Okay.
Sorry about that.
I believe the quiz was out of 14 points. Someone else asked that in the thing. Okay, 5.2. Here.
Oh, okay. Thank you.
Yeah, so we use the equation p prime equals minus rp. And knowing how to find r would tell you that none of the above applies.
Okay, thank you.
Any other questions before we wrap up? I forgot to look at your schedule just before class, so let me check that to see what's on the docket for today or before class next week. So next week, there is no quiz. We just have a Zoom Q&A session. We do a lot of things over that time, so you'd probably want to ask me about it. So today, or sometime by the end of this week, you want to get up to lecture 25. If you can get up to lecture 28 by the start of class on Wednesday, November 4th, that would be great. You can ask me some questions about that stuff too, because you do have a quiz the following week. So try to get up to lecture 25 today. Try to get up to lecture 28 by Wednesday next week. that would put you in a good position to ask questions. Technically, you don't have to finish lecture 28 by next week, but since you're going to have a quiz on that the following week, it's probably good that you actually just forge ahead a little bit so you can ask me any questions that you might have. For now, since I don't think we have any more questions, I think we're going to sign off. Apologies for the technical difficulties today, but that's how things work out sometimes. That's how it be sometimes. So yeah. All right, we'll stop there. I will look at the quiz. I'll release the grades, and of course, at some point, I'll update those into Jupyter. Remember, Jupyter is what you look at for your actual grades. You don't look in Gradescope because Gradescope counts the bonus in the total, which I don't. Right when I transfer it to grades to Jupyter, I change the total that is out of. I believe today's total was 14. There were 14 items that you had to answer on the quiz itself, and there were 3 extra points that you could get from the bonuses. All right, have a good day, everyone. Take care. Have any questions, you can email me, but we're signing off. Go and watch your lectures, and I will see you guys in the next one. Ciao.